We'll begin with an overview of how files are represented. Now, logically, we have a table with rows and columns, as in the relational model. And we map that into a file full of pages or blocks on the disk. Now, the table itself is made up of logical records, and the records themselves need to be represented somehow. They're represented in memory as arrays of bytes, essentially. And then those bytes are packed onto pages in memory. So the file's got pages on disk. Each of those pages can be brought into memory, and it contains a bunch of bytes, and those bytes represent records. So this gives you an overview. Obviously, we'll go through all this in more detail, but this is kind of how we get from tables to bytes on disk and bytes in memory. So as an overview, we've got files. Files contain pages, and pages contain records. Tables are stored as logical files in the disk space manager. The file consists of a set of pages, and the pages contain a collection of records. These pages are managed on disk by the disk space manager. You read and write them to physical disks and files. And of course, the transfer between the memory and the disk is part of what the disk space manager does. Now, in memory, these blocks from the disk are brought in and put in pages of memory stored in what's called the buffer manager, where they can be accessed as bytes in RAM. So the higher levels of the database are going to operate over the main memory representation of these pages stored in the buffer manager. Database files. Again, we talked about the database storing files and the files having pages and the pages having records. So let's start with what a database file is. It's a collection of pages, each containing a collection of records. And the API for higher levels of the DBMS is they can insert, delete, and modify records. They can fetch a particular record by its identity. So records will have record IDs inside of the database system that we can point to. Record ID you can think of as a pointer, and it encodes a pair, which is the page ID of the page the record lives on, and a location on that page in some sense. We'll talk about how we have distinct locations on pages shortly. Another API call that the higher levels will have is to scan all the records in a file, possibly with some conditions on the records to be retrieved, like a where clause type condition. And a file for the database, as we've said before, could span multiple operating system files, and even multiple machines. And in some cases, also as we discussed before, database files may be implemented without going through the file system at all. They may be implemented on raw disk devices. Now, files themselves in the database can be structured in a variety of ways. There's unordered, what are sometimes called heap files, where records are placed arbitrarily across the pages in no particular order. Another option is to have clustered heap files, where the records and pages are grouped into records of similar values. We'll talk about all these things in more detail soon. I just wanted to give you a sense of them. We also have, in principle, sorted files, where the pages and the records are kept in a particular sort order. And then finally, as we'll see later on, there's a variety of clever index files, which are essentially disk-based data structures for doing lookups on data. This includes B+ trees, linear hashing, other schemes. We'll focus on B+ trees later in this class. The index files themselves may either contain records, or they can contain pointers to records in other files. So it's possible to have files referencing other files. Indexes do that. So let's start by talking about unordered heap files. Okay. In an unordered heap file, we've just got a collection of records in no particular order. This is not to be confused with a heap data structure. If you've seen that in your data structures class, there's a data structure called a heap that supports efficient find min, right? Find the minimum object in the heap. That's a different data structure. This is just a file on disk with a collection of records in no particular order. And in a database heap file, as the file shrinks and grows, pages are allocated and deallocated. And to support these record level operations, we must be able to keep track of what pages are in our file, where's the free space on these pages so we can accommodate inserts, and where are the records on each page so we can go get them. Okay, so let's look at an implementation of a heap file implemented as a list. This is a simple implementation. The idea is that there's going to be a header page at some particular location on the disk, and so its location will be its ID, and there'll be a name associated with the heap file as well. And these pair of a name and an ID will be stored somewhere in the database. We'll call that the database catalog. It's got a place to look this stuff up. Now, every page in this heap file is going to contain 2 pointers, and then all the data pages will have some free space potentially and some data. The header page itself is just going to have 2 pointers, one to a linked list of full pages that have no more room for inserts, and one to a linked list of pages with free space. And so we have a doubly linked list of full pages, doubly linked list of pages with free space. And I said this is a simple implementation, and it's sort of got a fatal flaw. What is wrong with the implementation? Well, suppose you're looking for a page with enough space for a 20-byte record. Well, we know that we don't want to choose one of the full data pages, but which of the free space pages should we choose? The only way to know is to walk down this linked list of free space pages and see if one of them has 20 bytes. And we may walk quite a ways down that linked list before we find one with 20 bytes. So that could be pretty inefficient. We'd like to have a faster way to find a page that has capacity for our insert. Here's an alternative implementation which uses what's called a page directory. And in the page directory scheme, we're going to have multiple header pages. The first one will be stored in the catalog, but these header pages will be in a linked list of header pages called a directory. And in this directory, each page is going to have entries, and the entries will include a pair of the number of free bytes on a page and a pointer to that page. So for every data page, we'll have one pointer to it from the header page, and the header pages will keep a empty space, a number of free bytes associated with each page. These header pages are likely to be accessed pretty often because we'll scan through them. So they're probably going to be in the cache in RAM. So they're going to be pretty cheap to access. And then finding a page to fit a record requires far fewer page loads than the linked list on the previous slide. Why? Well, look, one header page here has the free space of many data pages. You know, this header page is just storing small pairs of a number of free bytes and the ID of a page. You can put a lot of those in a 64 kilobyte header page. So in a 64 kilobyte header page, we might have many, many pointers to data pages. And so odds are decent that you'll find one with enough free space very quickly. You can imagine optimizing this page directory further by compressing it or by putting it in a more complicated data structure. But it's unclear that it's necessary. With a small number of header pages, you've already covered a pretty large data file. So a reasonable implementation is the one here of a linked list of header pages. If you want to do something fancier, you certainly can. So in summary, we've got a table. That table is a logical object, but it's encoded on disk as a file, and that file itself is a collection of pages.